nossa reunião mensal. Hoje teremos a apresentação do Gaia Earth Adventures in Research for Wireline, Conveyance and Wellbore Diagnostics. O Gaia ele está baseado no Reino Unido e tem ficado envolvido nas operações globais de Wireline por mais de 30 anos. Metade desses 30 anos tem sido envolvido em projetos de Ph.D, né, na sonda, identificando problemas reais que têm uma grande valor para as investigações, né. O principal objetivo da sua equipe tem sido a identificação e mitigação de cable sticking and phishing em poços altamente desafiadores, em termos de NPT e emissões de gases. O sistema de produção de cabos tem funcionado com 99% de eficácia, né, nesses ambientes desafiadores, e tem dado para as operadoras a oportunidade de reduzir o risco já no planejamento ou durante a execução da operação por meio de isolamento dos cabos. Outros interesses incluem diagnóstico de poços e dinâmicas de cabos, incluindo validação da profundidade de testadores de formação e ferramentas de testemunhagem rotativas, por meio de matrizes de sensores montados nos cabos e ferramentas de wireline. Hi, Guy. Thank you for your presence here in the monthly meeting of the Brazilian chapter of the SPWLA. It's a big pleasure for us to have you here with us. I'm not going to take more time, so please start your presentation when you be ready. Thank you.
Thank you very much for the introduction, and to anybody who's listening and watching, welcome. It is great to spend some time together and to talk a little bit about some areas of research that we've been doing for the last few years in wireline conveyance and for you. So today we're going to talk about three areas of discussion. The first one is how to assess and de-risk wireline sticking and fishing on challenging wells. And why is that? Because cable fishing is one of the most NPT intensive and hazardous activities in wireline operations. And 15 years ago, I started working on this problem to predict it and to solve it. And I'm happy to say it's now 99% predictable and avoidable. The second thing is about depth control for formation testing and rotary coring, that is on wireline, of course, and why I think that we need a new protocol and also some new technology. And that work comes out of a digital standoff, which is clamps on the cable, and it's got a sensing package. And it's telling us what the cable and tool is doing downhole during a survey. And we found out some very interesting things about cable dynamics that impact the depth control. And I can tell you that in some wells, this idea of depth control is really quite troubling, because we are not in control of the tool in some scenarios. And so I think we can do a much better job on probe and core bit positioning through bespoke procedures, downhole data, post-job corrections, and new procedures. And then lastly, I'm going to talk about a new approach for temperature logging with a continuous extrapolated temperature log, because in the post-mercury era, where it's very hard to get hold of mercury thermometers, continuous temperature logging can be a lot more rewarding for formation evaluation. And we are also using that in fluids modeling to look at cable drags and tool drags to try and explain what is going on in terms of cable dynamics. Okay. So the first section is how to assess and de-risk wireline sticking and fishing on challenging wells. So a little bit of basics about wireline here. If you imagine you have a platform, you have a logging unit, a winch, you have a couple of shivs, there's a cased hole section, and then there's an open hole section, and there's a tool at the bottom of the well. In this case, it's a tangent well, and when we pick up to move that tool, the cable pulls into the formation. Okay, and this is called cable thrust, and we compute that. And basically cable thrust or cable slot cutting is the root cause of all cable sticking. If you're cutting through mud cake, you can end up with differential sticking. If you're cutting into the rock, there are various mechanisms that can then trap the cable. You can have reactive shell swelling, you can have ball stress, you can have mechanical binding, and if it's permeable, you can have differential sticking, or any combination of those things. So naked cable, it acts like a big saw cutting through the dogleg zones in that wellbore. Okay, so the question is, what are we cutting into and by how much? And you can see some pictures here. This is a spiral hole. That's a cable groove that's been identified with an ultrasonic imaging tool. You can see a cable groove here. It's on the high side of the hole. It was very bad cable stick slip that was upsetting the log data. Not tool stick slip, cable stick slip. And then this came out of a coring tool in the Far East. You can see the cable groove quite clearly. We predicted that there might be a problem with cable sticking on that job. And in fact, there was cable sticking, but they didn't have any wireline standoffs available. But it was a very nice kind of endorsement that our modeling was correct to get a piece of rock with a groove in it. Okay. The cable thrust is affected by primarily the wellbore trajectory, the dogleg severities and sequences in a directional well. The cable weight, because a heavier cable, you've got more tension, more thrust. The cable drag coefficient is the same argument. And then the tool string weight or tool string sticking. And this is a very important point, okay? If the tool gets stuck and you start working this cable to try and free, the character of the cable thrust stays the same, but the magnitude increases. And what you can find is that as you're working this tool, and then you pull and hold, because sometimes tools do pop free at the 11th hour. We've all seen that. When you slack off, you can't pull free. You slack off to burn off the cable head down here, you find that the cable is stuck. Okay, so there is a thing called sticking linkage, and we need to assess that. So in our modeling package, we assess the cable sticking risk by looking at the thrust distributions across the whole open hole interval. So what sort of wells and jobs are risky? Well, for key seeding, you've got tortuous wells, directional wells with a lot of open hole work with weak to medium strength formation over the build, the drop, or the turns in the open hole section. Typically, you're looking at UCS 5 to 6 kpsi or less. Dogleg severity of the build, turn, or drop 2.5 to 3 degrees per 100 foot. But what I can say is that wells with long open hole sections increase the slot cutting. So if I had a well that had a 3-degree dogleg building to 20 degrees, okay, and I had a 4,000 foot interval, I could get the same slot cutting if I had a lower dogleg severity but a longer open hole interval, because there's more cable passing through that dogleg zone. For diff sticking, you don't need much tortuosity, low to medium over permeable formations, or you've got loss zones in the well in order to cut through that mud cake, reveal the pressure imbalance, and then you can find that the cable is differentially stuck. Many wells that we assess have got both diff sticking and key seeding. The ideal is to drill a straight hole through the reservoir, and then you are largely punching out the diff sticking. If you are dropping over a reservoir, turning or building, you are baking in differential sticking risk into your well design. And we do a lot of work with clients on optimizing well trajectory to reduce sticking risk, either key seeding or differential sticking. You can also have wells with a proven history of sticking, and maybe you've migrated to pipe conveyed logging or LWD and you'd like to go back to wireline, and we can use that data to build a benchmark. If you're on land, you might have water-based mud, limited pull with a logging truck, and you may have kinks outside the shoe. We've seen this many times. So the driller comes out of the casing shoe, he's adjusting the weight on bit, the mud pumps, the RPM, realizes, oh dear, I'm not vertical anymore. Then they bring the hole back, and then there's a dog leg. And if there is a sand aligned with that kink, may have differential sticking risk because of that alignment. Okay, if you've got long jobs with many logging runs, you've got cumulative slot cutting, and also there are papers talking about hole deterioration affecting the sticking risk, not only for cable but also for tools. If you've got a lot of jewelry on your tool string, that can disrupt the mud cake as well, and then the cable can be exposed to the formation. If you've got extensive formation testing and sampling operations. So when you pick up for a pre-test, every time you do that, you're cycling the cable over these dog legs, you're cutting into it. And we've seen quite a few times, you start off with a pre-test survey, after 20, 25, 30 pre-tests, you start to see the onset of cable sticking because gradually you have disrupted that cake from SAMs further up the hole. Okay, and then that sticking, it may stay the same or it may get worse. Okay, deviation is a factor, but it's not as important as open hole tortuosity. If it's a deviated section, then this tool string jewelry can damage the low side of the hole, and then you can have problems. But it's not as important as people might think. And you can see a selection of wells here. These are the casing. These are the open hole sections. These are the cable thrust vectors that I was talking about before. Okay. And these are the open hole sections colored according to the dog leg intensities. All these wells had offset sticking or fishing. All of them were logged successfully using cable protection. So we identify the sticky zone on a well like this. It's this section here. We put standoffs on the cable over this zone. So when you're sampling down here, the cable is going to stay free. Okay. So those are the more interesting wells. These are key seating. Some of them have got differential sticking as well. But these wells on the end, these are near vertical wells. Okay. There's been bad cable sticking on all these three wells. Okay. And so how can that be? I mean, they're fairly straight. Well, you don't need big dog legs in order to cut through mud cake. Okay. So differential sticking, you may need to TD the well before we can do a detailed sticking risk assessment. But for key seating, you can generally do it, well before spudding, months in advance. So if we go back to 2007, I was working in the North Sea, supervising a project for an Exxon, and we're having a lot of repeated cable sticking events. And all I could do as the wireline supervisor was say, yes, we've had sticking, and we're probably going to have it again. And all we can do is pull. So we didn't know when it was happening, when it was going to happen, why it was happening, and there was no intervention possible. The only thing you can do with stuck cable is pull on it. Okay, so I started with 3 clean sheets of paper. Definitely we need to do something with the cable. We need to clamp something on there to get it away from these sticky zones, like a stabilizer on drill pipe, okay? We need software to be able to analyze the tensions and the thrusts, and then we need a benchmarking system to decide when do we have a risk and when do we need to make an intervention. And so the system that we developed through this research is that we can evaluate accurately the cable sticking risk on all these wells through detailed systematic engineering analysis. And I can tell you all 4 wells had predictable sticking and preventable fishing operations. Differential, diff key seating, and key seating. Okay. And in hindsight, having done many postmortems worldwide, I can tell you many cable fishing operations are inevitable by design. I'm talking about well design and wireline job design. Okay. If you have a well like this, okay, you've got a very long open hole section. You've got dog legs here. You've got sands across here. You've got low UCS rock, and you've got 5, 6, 7 runs of wireline. You are going to have a problem. Okay. We know that now. So over time, we have built a database of problematic wells and jobs around the world. The more data we have, the more sophisticated our analysis has become, the better the decision making and the recommendation about whether or not you need to be running wireline standoffs. I mentioned before, cable key seating can be evaluated months before spudding because that well profile is not going to change too much. There will be additional micro dog legs on top of the projected data. So the actual open hole tortuosity is going to be higher than what the projected plan was, but it's enough at that early stage to tell you whether you've got a key seeding risk. And 90% of cable fishing operations are with formation testers. Why is that? Number one, there's usually a couple of logging runs prior to that do some damage to either the formation or the cake. Okay, so you've already got a slot by the time you're rigging up your sampling string. It's the heaviest tool, and you're stationary, and you may be doing an extensive pre-test survey, a lot of cycles, a lot of slot cutting, and then you sit there on the first station 3-4 hours, bam, I'm stuck at the end of it. And fishing stuck cable is more common than coming free. The odds are slightly against pulling free. It's like the casino always wins, so you're more likely to go fishing than you are to pull free. And the question that clients have is, what risk do I have on my next wireline job, and is an intervention needed? And a lot of our time is spent doing that, not deploying standoffs, but doing risk assessments, monitoring jobs, and making sure that by the time they get to TD, there are no surprises waiting for them. So if you don't have cable protection as a system, you've got no risk assessment, you've got no foresight on what's going to happen, you've got no barrier to NPT associated with cable sticking. I'm not talking about pulling out of hole, I'm talking about having a wiper trip, about going in again on wireline or going pipe conveyed logging. The NPT can roll up very quickly when you've got cable sticking. It's going to be a reactive response. It's always a surprise. Okay, what are we going to do now? Phone calls at 3 o'clock in the morning, and there can be a pretty big cost potential. Anything from 1 day to a wiper trip to 40 days for a cable strip over operation that went wrong, and then the cable parted, and then you've got to go in and fish out the cable. So if you look at this well here, it's near vertical, looks pretty benign. There's a small kink in the middle of the well that is not enough to get cable key seeding. We know that, okay? But cable was fished on this well, okay? Because there was no risk assessment, no cable protection. So this was a post-mortem assessment. And down here we have a reservoir where the cable got stuck. We could have deployed 22 standoffs. These are the little dots here. This is the cable, this is the tool, this is the reservoir. So 22 standoffs could have been deployed, and near guarantee, no issues. You'd have got all your data, and no 3-day cable fishing operation. Okay. If you do have cable protection, you've got a proven engineering process at work. From the moment that you decide on your well path, you can do an initial risk assessment, and then as you're drilling it, we remodel. Some wells we model 4, 5, even 6 times. So you can avoid NPT, wiper trips, pipe conveyed logging. Generally, we're saving about 40 hours per job. We did a project in East Africa. We saved per well 2.5 days through cable protection. Complete elimination of pipe conveyed logging. No sticking, no wiper trips. It was a very good success. It's going to be a smooth operation. It's going to be a clean operation, and it's going to be efficient acquisition. Basically, everybody's going to be happy. The client's going to be happy, the logging provider, and we're going to be happy because we're doing something useful. So this is a well here that we logged earlier on this year in the Gulf of Mexico. You can't see the sands in here. I can't show you that, and I can't show you the depth. But you can see it's very tortuous, high dog legs. You've got a lot of sands aligned with high thrust. You've got high key seeding risk, high differential sticking risk. We ended up deploying around 100 standoffs. It was a very successful operation, and we saved at least 1.5 days, which is reducing the emissions significantly, okay? So we've done some calculations, and a deep water rig, the average fuel consumption of diesel is around 275 barrels a day. It turns out to be around 5 tons of CO2 emitted. That's not including any scrubbers if you've got, cleaning on the rig, but it's saving around 175 to 180 tons of CO2 by saving that day and a half and using cable protection. We've done almost 100 postmortems from around the world. And really the common denominator is just there's no oversight in cable sticking risk. So a job like this, there's no assessment. It happens. We do the assessment. It turns out that there's 170,000 pounds sticking potential down here, and the overpull capacity with the cable is around 6,500 pounds. Those are horrible numbers. You should not be logging that without cable protection. Okay. So the software we use is called WirePro. We developed this, as I said, from scratch. It's been a big investment for us, and it's grown arms and legs over the years, as it had to. Okay. So we have a spider plot that tells you about key seating risk, differential sticking risk. We've got a nice schematic, the usual tension plots and available pull limits. We do cable stranding risk. That can be an issue. If you're logging a new cable and you're cycling the wire, you can end up stranding or popping an armor, and that can take 5 to 6 hours of rig time to swap the cable mid-job if you have to go that way. We give you the sticking potential it's a to-scale drawing, and it shows you the thrusts and the sands. It tells you how much differential sticking you can tolerate, how this well compares for key seating and differential sticking. And then we've got a list of triggers about whether or not we should be running wireline standoff. So well site experience trumps modeling every day of the week. Okay, the modeling is useful, but we need to factor in what the subsurface team are saying, what the drillers are saying, what their concerns are, and then we arrive at a decision, and then we can design a deployment plan. We have an extensive sticking database for wells where we've run standoffs, where we have seen sticking and pulled free, and where there's been fishing. We've got 277 records in there from around the world. The more data we get, the better decisions we can make for clients about whether they need to be running standoffs. The standoffs themselves, if you do imagine logging cable embedded in mud cake like this, the projected area is really quite big, you know, and the pull to free force is related to the overbalance, the sticking coefficient, and the projected area in the cake. So without standoffs, you've got naked cable embedded in cake over time. If you've got standoffs, you've just got a small footprint every 50 feet, 75 feet, or 100 feet, or whatever the space out needs to be. So you're cutting your cable contact down by more than 99% in every hole size. Okay. So that's how you're mitigating differential sticking. And we've logged this up to 9,500 PSI overbalance. It's been fine. If you think about key seating, so you've got a groove in the rock. If you have a standoff, it's not going to fit in that groove. You're not going to get stuck. So you're above the cake and you're above the slot. And that's why the technology works. Okay, so the standoffs come in cases of 12. They're steel bodies. They come in different sizes. We have 18 different cable insert sizes. These are made from aluminium. So you look at the cable on the job, you measure it, or you look at the spooling records, you select the inserts, install in the steel bodies, and then you deploy on the cable according to what the software is telling us for a deployment plan. And we have an express kit. We've been building this with certified torque drills for the Gulf of Mexico. And this is our standard kit now in the Gulf of Mexico. And we have a portfolio of standoffs. These are mechanical ones to mitigate sticking. We've got K-stall ones to reduce drag and increase the available pull on the cable head. And then we've got sensing standoffs. So this is the one called WXSO. It's a digital standoff. It's got a small sensing package with pressure, temperature, magnetometers, and accelerometers, and it's telling us what's going on with the cable during a logging run. And this is what's telling us what's happening with the depth for formation testers and coring tools. So we're going to be talking about this later on. So our activities really are day in, day out, we're doing wireline conveyance risk assessments using our sticking database, now using a fluids database. We've got about 300 mud reports from around the world. We're trying to, so if you tell us we've got a 12-pound mud, we can look at the viscosity of that mud and then see how your mud is faring compared to other people who are using the same weight of mud. Okay. The second thing we do is wellbore trajectory optimization. You could be a sidetrack and you've got 3 different options, and we will tell you which one is the least risky, which one needs either no standoffs or minimum standoffs, and which one might need the maximum standoffs according to what your objectives are in designing a well trajectory. And then the last thing is the wireline standoff deployments. We have a base in New Orleans that supplies standoffs around the world for projects. And so we've got the sensing, the open hole standoffs. They come in different sizes because you've got to be able to strip over. So the standard size is 2.95 inches. If you're drilling with a 6-inch bit, 3.5-inch pipe, you'll need this 2.15 inch because you've got to be able to strip over this to get down to the tools. And then we've got the cased hole standoffs. Around 70% of deployments are with formation testers, about 25% with coring tools, and 10% are the other. And then these are the stats. It's about less than 3 minutes to install and remove a standoff. We space them out between 25 and 175 feet. The average is 55. We've run anything from 3 to 132. The average is around 44. And we've done deep, hot, high pressure, very low UCS, and high overbalance. And we're working with 25 clients in 14 countries, currently 370 deployments. We deploy around 20% of the wells that we're modeling. So 80% of the time you don't need us, but 20% of the time you do. Okay, and we've put over 15,000 standoffs in the hole with 99% efficacy now. So that's the summary on cable protection. We are doing some modeling in Brazil in the coming months, and we did some about 2018, 2019. But I think there's a good opportunity there to de-risk these logging operations, especially deep water jobs, by doing some upfront modeling and risk assessments. So the second part of the talk is about protocol for formation testers and why we need some new technology. Currently, the protocol goes something like this. Okay, I mean, you have to tell me if it's different in Brazil, but you take the tool, you zero at the packer, and you run in hole. You tie in around the top station. You might do a stick test if the client wants to do one, I don't know, 15, 30 minutes, and then you will commence the survey. You might do some creep correction to dial in offset. So in the Gulf of Mexico, some clients do that, some of them don't. And so what creep is that when you stop the winch on station, there is a period of time where the tool continues to drift up hole until the tension equalizes. Okay, that drift could be 1 to 3 feet, something like that. So in the Gulf of Mexico, they will do a test. They may either use the accelerometer in the tool, or they will stop below shale 3 feet. They will look at the raw counts. If the raw counts increase, at 3 feet, okay, then we're going to use 3 feet because that's how much the tool is drifting up hole when we come and stop on station. Then you're going to do the survey. Usually it's top down, but you could do it bottom up. So generally people finish the pre-test, retract the tool, slack off, go down hole, and then pick up to the next one. And the next one, of course, is deeper than the one you just did. If there's a tight or lost seal, sometimes it says in the logging program, move down 1/2 foot, 1 foot, so they will drop off, and then they will pick up, and then they will try again. Usually, every 5 to 6 tests, you'll recorrelate, unless you've got a big overpull, and then you'll recorrelate right away. And then you QC the data as you go. It's a focus on test quality, drawdown parameters, build up, repeatability. How is my DP by DT? Do I have a good final build up pressure? And in my experience, you're going to get 5 to 6 pre-tests an hour, including a correlation. If it's reasonable permeability, if it's low perm, you could be up to 45 minutes a test or something like that. And then after the survey, maybe drilling will ask you to log out hydrostatic if they're interested in the mud column. Maybe you've got a mud cap and they want to have a look at that. And so, I picked this off LinkedIn. I don't know whether it's real data or fake data, but it was a discussion about the free water line. But you can see that they've picked some gradients here and contacts through these pressure points. So the problems are, the depth is not corrected post job. You can get a lot of depth scatter, and we live with that. Okay, the only indication that there is QC is while we correlated and we're on depth. But per test, we can't be sure what the depth is. Creep is an optional single correction that sometimes gets done in the Gulf of Mexico, and I can tell you it's like a broken clock. It's right twice a day. The creep is highly variable. And there may be no quality waypoints on that gradient line via multi-probes. So if you ran 2 probes and you got a good test on one and a good test on another, okay, and your depth control was good, you can be sure that out of all these points, the delta TVD on these 2 points was correct. So I would weight this line according to that multi-probe data, okay? But there's no guarantee you're going to have multi-probe data. And we assume that all stations remain on depth between the correlations. So if you've got 6 top-down pre-tests between correlations, that's going to be 12 winch movements, 6 down and 6 up, and you can have up to 30 transients. This is really important. This is what we found with our digital standoff. And a transient is where the winch and the tool movements become decoupled. So you're spooling off or pulling in cable and the tool is not moving. And that can be through lags when you're moving off station, stretches when you're trying to get the tool moving, springs once the tool springs free, and then creeps basically whenever you stop the tool, either going uphole or downhole. And the protocol has been unchanged for many years. What we're looking for is better answers, more confidence, less scatter, less rig time, and less emissions. So we thought that by analyzing movement and creep on every station, we get a creep measurement here, 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 and here. It would be a good contribution to try and move this depth quality forwards using our digital standoff, okay? And so here's a close-up shot of the WXSO. This is the sensing package here. This is mounted on the cable about 30 to 50 feet above the cable head. Okay, so this cable is stiff. If the tool is moving, this is moving as well. And as it moves along the borehole, it picks up noise with the accelerometer. So it's like a seismic shuttle, one could say. It's monitoring the tool movements downhole through the accelerometer response. And if you look at the creep here, say we wanted to stop, we wanted to stop here on this, where this red line is. If you stop on that line, there will be creep and the tool will creep up hole. This is the winch driving, and this is good winch driving. Steady speed, on with the brake, and it stops. And the WXSO records the noise as this thing slows down after the winch has stopped. And as we said, it's between 1 and 3 feet, okay? If you correct for that, then you will stop down here and you will drift up here so that you're on depth. During all this research into the creep, we found a thing called anti-creep, okay? And anti-creep is where the tool will stop way before your target. We've seen it up to 8 feet. And this is the winch driving, okay? And so 10, 15 feet before the station, the winch is going slower and slower and slower because the winch driver is trying to do a perfect job. They're trying to get that digital dial read perfectly 18,751.5 feet. Okay, and that's easier to do if the winch is moving slower. Okay, but what happens is when the tool is moving really slow, it can get grabbed by the formation, and then you can stop way deep from where you're supposed to be. So this is good winch driving, you've got creep. This is bad winch driving, you've got anti-creep. And we've seen up to 13 feet depth discrepancy, minus 8 feet of anti-creep and plus 5 feet of creep. So I'm going to show you a typical creep report. So it's a batch file. It's very nice to process. The tool knows when it was stopped, what time, what depth, what the speed was coming up to station. how long they were stopped. This is the winch profiles, good winch driving. It looks at the noise for 60 seconds before it's stopped, and then you've got a decay signal of the noise. You can integrate that noise and you can get a creep depth. Okay, and we've got an inclination. We also look at the head tension. What we've seen on some jobs is if you run a hole down to a station, you start to set the tool, the probe becomes centralized, it can drop down a hole a few feet. That's why we monitor the head tension to make sure that that is not happening. So we've done around 45 runs with WXSO. We picked 8 jobs from around 16,000 to 30,000 feet, deep water jobs. And these are the creep distributions. And the average was around 1.6 feet. But you can see that 3 feet that is used on every station, it does not represent what is going on. There's a lot of variability. Okay, so creep is very common, but it's really the value that has been chosen as an offset before the survey commences. Anti-creep can prevail with bad winch driving. We've seen jobs where the winch driving is wrong from the first station to the 50th station because the technique is wrong from the start, and they keep slowing down on every station. So every pretest is deep from where it is supposed to be. And what we've learned is that creep is only of use if you're on depth, 100% on depth, in real time, steady speed, tied into the correlation log, and it's an abrupt stop on the station. We can't predict creep from the well parameters. One would have thought that you would get more creep on a deep well. There's just, we can't tell you, okay, it's a tangent well, 25,000 feet, 13-pound mud. Roughly your creep is going to be, 2.5 to 3 feet. We can't do that, okay? And we studied it, and it's like, okay, let's take a time out. Let's step back. There's something going on here that we don't understand. Okay, so that's what we decided to do, and we discovered these transients between the station logs that can impact the tool position far more than the creep distance. The creep can be the tip of an iceberg for depth discrepancy, and so what we've been doing is measuring the dead time as a percentage, and it's a measure of the tool and the winch decoupling per station, and that's defined as 1 minus the tool motion over the winch motion. If you imagine a 300-foot vertical well with brine in it, if you slack off a few inches, the tool's going to move a few inches. The tool motion matches the winch motion perfectly. The dead time is 0. But if you have tortuosity, okay, if you have depth, if you have viscosity, there's so many parameters, then you are going to have some dead time. Creep is one of the dead times, but there are other things as well. Okay, so I'm going to show you with some schoolboy animations here. Say you've got 2 sands and you want to take the pressures in those sands. What are your options with winch control? What are the transients and what's happening with the dead time? So the first option is I'm going to move down off station. I'm going to go to my second sand. This is a top down, logging down. In this case, I've got 2 transients. I've got a lag, so I'm spooling off, but my tool isn't moving. It starts to move, I stop, and then I've got a creep down at the end of it. Okay, the tool motion is not connected to the winch motion when it's decoupled during these transients. The second one is bottom up. Okay, this time I've got 3 transients. I've got a stretch, I've got a spring, and I've got a creep. And then the usual one that we're using, which is the down-up method, you've got up to 5 transients. 1 lag, 1 creep, going down, 1 stretch, 1 spring, and 1 creep or not. If you're not driving the winch properly, then you're not going to get a creep up there. You're going to get anti-creep. And the reality is something like this. A lot of winch movements, okay, and maybe not so much tool movement. So the pre-test, I'm talking about depth confidence here and the logging protocol. The tests with the least depth confidence are those with compounding transients, the most dead time. If you switch your survey direction halfway, you go from top down to bottom up, you're probably going to skew your gradients. People already know this, but it might be a lot worse than what we thought. This business of dropping down and picking up for tight test could be unreasonable and a poor utilization of rig time given the depth errors that are possible. And the tests with most confidence are those with one transient. It's creep with minimum dead time. So you're actively on depth. It's a real-time correlation. Steady speed to station, same speed as the correlation pass. Stop on target. If you want to factor in 1.5 foot, you can do that. If you've got some data, you can do that. All right. But that minimizes your dead time because you're avoiding these big tension swings that are causing problems. So a rethink on station logging protocol would factor in a few things: well depth, tool properties, hole conditions, cable and tool stiction. Stiction is static friction. Okay, tension transmission efficiency, which is 1 over the wireline tortuosity. Tortuous wells, it's harder to get the tension down to the cable head, right? Mud properties, viscosity, gel strength, fluid bypass. Spacing between stations. If you've got a big lag distance and a short distance between two stations, there's no point in just moving down from one stand to another. The tool isn't moving, okay? So there's a lot of trade-offs in job planning on rig time between when should I be doing correlations, how do I manage these transients, how am I going to acquire all this pressure data in the most efficient way and with the best confidence and the minimum scatter. Definitely multi-probes with a fixed delta MD and TBD provide you quality waypoints for gradients. So I'm going to give you an example of a deep water well. It's about 17,000 feet, tangent section. And we did about 35 stations. This is the dead time, okay? And then this is the percentage of tests. Around 60% of the tests had more than 30% dead time. So the winch is rolling, but the tool is not moving. And there was 4 stations here where the tool didn't move at all, okay? And so we compared that. This is a very high plastic viscosity in this well. Somehow this is related to a time constant for the winch movement. Viscosity is certainly one of the factors, because if you have a damping system, if you increase the viscosity, you're slowing things down, okay? But I'm going to show you a couple of examples of a 70 and an 80% dead time. What is driving this variability? Winch driving number 1. An E-winch would eliminate one big variable. The cable has mechanical memory. Maybe you had an overpull coming up to the last station, and it remembers that when you slack off the next time. Whatever you just did on the winch, it affects the next move, okay? Complex contact mechanics. This is where the anti-creep comes in. When you slow down and you're shifting from a dynamic friction coefficient to a static one, that is a very complex thing. And it's happening with the cable, it's happening with the tools. You've also got complex fluid mechanics. You've got these gelling and break cycles throughout that survey. And it's a 17,000 foot serial spring damper system, and every element is in constant flux. So there's no wonder that in this situation we've got a lot of variability on our depth. So the first station here, we've got 80% dead time. We're moving down around 27 feet, and then we're picking up around 19 feet. So the winch starts. We think we're moving downhole, but we're not. There's no noise, no change in the pressure. We spool in about 21 foot, and then the tool starts moving. We can see the pressure kick. The tool starts moving downhole. Then the winch turns around, but the tool keeps going downhole as the winch starts to come uphole. And then the tool basically stays put. We're coming uphole 19 feet, but the tool didn't move an inch. It stayed downhole because of tool stiction. And then the winch stopped here. So we think we probably stopped around 11 feet deeper instead of the 8.1 feet that we were looking for. So this is a good example. So the tool moved for 20 seconds, the winch moved for 104. It's an 80% dead time with the winch and tool decoupled. Second example, tight test. We're going to move down 23 feet. We're going to pick up 22.5 feet. A lot of lag. The tool starts moving. The winch changes direction. It continues to creep downhole as the cable is coming uphole or spooling onto the winch. Then nothing happens, then it springs free, it's in sync with the winch for a while, and then the winch stops, and then we have a fair bit of creep at the end of it. So we think we're shallow in this case. The tool moved twice over 36 seconds. The winch is moving for 112 seconds, 70% dead time. Now, 70% of the tool movement is from creep. It's not from the winch. So it's like you're touching the tool, and then it's off, and then it's going to stop when it feels like it. So in this case, we are not in control of the tool. So what we can do with our digital standoff is come up with a depth quality classification. For every station, we can look at winch movement, depth, head tension, line speed. This is a good test, okay? So we've got a little bit of lag at the beginning. We're moving down 65 feet between stations. This is the noise on the WXSO. The winch stop is pretty good. There's a little bit of creep at the end of it. It's a reasonable test. We can adjust the thresholds, but this qualifies as a good test. This is a bad test because the tool didn't move at all. They tried to move downhole about 2 feet over 8 seconds. Okay, what we can then do for a whole survey, look at the movement types. Is it up? Is it down? Is it good, bad, or marginal? We can look at the lag picking up. It's around 6 feet before it starts moving between stations. Dropping off is anything between 5 feet and 21 feet before the tool starts moving. Okay, and then we can get histograms for dead time, for winch slow speeds. We want you to stop that winch in less than 5 seconds. Okay, and then we've got a creep time and then creep histograms. So this is a very good step forwards, but we still need to measure the tool movement directly. We're inferring this from the noise and we're integrating it. What we want to do is to measure the tool position using an odometer downhole. That's what we're doing now. The tool is in New Orleans. We're preparing it for field test. It's a WDI, Wellbore depth instrument. It's got a couple of articulating wheels on Scott Russell linkages. It's sprung loaded to press down, a few kilograms of force to get grip, and then the wheels rotate. So you've got 2 wheels independently sprung. Inside the wheel is a sensor that counts the rotation, the direction, and the speed of the wheel. So it's a micro logging package. We designed this from scratch. It's about 1 inch diameter, 22 millimeters deep, and it will log for 6 days at 30 milliseconds. And it logs in accelerometers in 2 axes. You've got a y-axis and an x-axis. Okay. When it's installed inside the hubcap, this is what it looks like. And the signal you get looks like this. Okay, so you've got a phasing between the 2 XY accelerometers. If you look at the frequency, you've got the speed. If you've got the phasing, you've got the direction, downhole or uphole. And then if you count the turns, because the circumference of that wheel is 1.44 feet, you can get the distance traveled, including during transients, which is what the purpose of this thing is. And so we can get a good point-to-point distance between stations. I tested the sensor on a kid's stabilizer. I took it around the park. This was a tilt test, so you can get relative bearing from it as well. And then the park in London has got all sorts of different terrains, much like you might find in a borehole. And we managed to process all this before we invested in the hardware. I wanted to make sure that the software and the acquisition system was going to be okay. So it's a slip over tool. You can run it on a coring tool. You could run it with a tractor or a formation tester. You've got 2 depths independent of tension and winch. It's an alternate depth channel, you could say. You're up on all 0 at the shoe to TD. There's a CCL and a pressure and temperature sensor underneath these little fins here, so you can get the casing shoe and then start measuring the depth. If you found a discrepancy of, say, 20 feet between LWD and wireline, if you ran this tool, you would have an alternate view on what might be wrong, okay, in terms of the depth. So you can get a in situ casing tally from the CCLs and the wheels. As I said, point-to-point distances will give you DMDs and DVDs for pressures and also cores, and the resolution along hole is less than an inch at 1800 feet per hour. And also, if you put a WXSO on the cable, then you've got two pressure measurements. It's a long spacing gradio for fluid ID. So a new protocol for station log, you need to design logging procedures that are specific to the well environment based on depth, tortuosity, mud properties, and offset cable dynamics. Run a WXSO, observe your dead times, traffic light QC for post-job QC, run a WDI, we're field testing it soon. Logging down, minimize your tension transients between stations, correlate on the fly, be on depth before every station. You want to isolate the creep transients. Don't stop, don't pick up, don't go downhole. Just keep moving at steady speed on depth to your target and then stop abruptly. Probably discontinue this process of going down and picking up plus or minus alpha. It's a waste of rig time, I would say, until it's proven otherwise. Okay. And multi-probes would be fantastic for more quality waypoints, okay, on your gradients. If there was a tool that had 5 serial probes, 1 hydraulic section, 5 probes, variable space outs, it'd be fantastic. You set one, you can set other ones. I'm damn sure the pressures are good. I know that I'm on depth, and I know my delta TBDs. That's going to weight the quality of my gradient, okay? Single probe is a standard, but it's the worst case scenario for gradient errors and survey efficiency. I think we can do much better. And you can correct your MDs and TBDs post-run and update the procedures for the next well. Cable dynamics, tool config, winch survey, winch tactics. You know, you've got to iterate your way towards success. You know, many logging programs drop off 20 foot, pick up. You know, it's one size fits all. It doesn't work in that deep water, tortuous environment, okay? Also for rheology, we want triple temp mud rheologies. There should be 40F, 100, 150. Get the full mud density, get the full temperature logs. We can do some advanced fluid modeling, which is what we're doing now. So we're computing how the gel breaking force is affecting the cable and the tool between a 10-minute pretest and a 30-minute pretest, because that's throwing you off depth as well. So clients and loggers need to work closer together, do an analysis of your gamma ray. What would be the ideal pairing of probes in order to get maximum bang for buck during my survey? It could be 2 probes, could be 3 probes. You know, look at the mud analysis, look at the cable dynamics, the lag and the creep estimates, define your probe, running hole for optimal acquisition. Okay. So that's the second part finished. The last part is about, I'm going to have to go through this because I'm running short of time. It's about continuous temperature logging. And so mercury thermometers are now banned in many places. The data can be erroneous. We assume that the max reading was when the tool was at TD. Cable head was 150 foot above TD. That is certainly not always the case. You can have hotter zones in other parts of the world, some distance from TD. Some thermometers are just plain hard to read. You've got massive temperature scales. It's the only thermometer you've got. You know, what is the error when you're punching that into your Horner estimate? So continuous logs, definitely the way to go. But there are some factors to consider. The type of sensor, the range, the accuracy, and the resolution. Is it calibrated in an accredited lab to a recognized standard? Is it validated at temperature? How is it tested? Have you got electronics drift? Have you qualified that? Is it an issue? Is there a pre-job validation available? Is it an internal measurement or external? Should be external, exposed to the well fluid. And where is it on the tool string? Close to the bottom nose is best. And what about my turnaround time? Generally, you don't have much time. If it's on the bottom nose, you have to take it off, download it, and then the bottom nose is needed on the next run. And ideally, you're using the same sensor. Okay, is it time depth converted, or is it just time and temperature in an ASCII file? And then what processing and what QC is available? So using our digital standoff, we've come up with a continuous extrapolated temperature log. It's this red curve you can see here. So these 4 runs on a deep water job. This is a seabed. Because we know the exact position of the WXSO and the times in circulation, we can run a Horner computation every 10 feet and end up with this red curve here. And then the pink banding around it is the error bar on the linear fit of the Horner data. It's unique to our industry as far as we know. You get a temperature every 10-foot TBD. And you can also get a temperature gradient from that in measured depth that you could then put into your large composite log, which is usually stuck on the wall, and it will help with the interpretation. So this is a good development if you're looking for accurate extrapolated temperatures. We're also asked to convert some temperature subs to continuous temperature loggers. We did that. We took these, we machined them, we made sensors, we made a logging package. It's in its final phase of validation now. It can be as a bottom nose, or you can have a sleeve with a hole finder connected, or you can stack them if it's a hot hole and you want redundancy. So it goes to the bottom tip of the spear. It's calibrated in a QMS in a UCAS laboratory in the UK to the British standard, to the international temperature scale. I don't know how we could qualify it more than using all these different standards. And we've done a shop validation in a circulating oil bath to avoid hotspots to check for electronic drift. And it is compatible. When we start running this, we're going to be using CETL logging as well. And the heat cycles are going to be downloaded every time to come up with a junking policy. And we can also flash this for 8 to 18 hours up to 250 C. We've also got another one called FTSO. It's a fin temperature standoff. This is it. The prototype is being made right now. This is actually an open hole PL sensor platform, so you can slide different sensors into this fin. Temperature is we have that finished now. Interested in density and interested in a spinner. What's happening to the fluids when you're cleaning up during formation sampling? Be pretty interesting to put these on the tools, see if we can detect pump fluid. Okay, you can use this in an 8.5-inch hole or more. Put the fin to the high side, and you can load a bunch of fin carriers on tools offline, and then just insert that on the rig floor. It's got a lanyard hole there, so it's nice and safe. And you can put it on 3 3/8 or 3 5/8. Smaller thermal mass than a TNOS, and there's a gap there, so you're not getting tool heating into the body. And that's the FTSO. So in summary, I'm sorry if I'm a little bit late, but from the three areas that I've been talking about, in terms of conveyance risk assessment, the best time is the same day that well path 1 is defined. De-risk the well design through iterative modeling is the best option. If trajectory changes can be made, if you can do that, drill a shorter open hole interval, put your dog legs behind casing if you can, or more dog legs behind casing, slower turns in lower UCS rocks. You can do harder turns in harder rocks in order to tangent your reservoir. As I said before, if you're building, turning, or dropping over your reservoir, you are building in risk. And if you push your dog legs towards TD, you're also reducing your key seating risk. But if you can't do any of that, if that well profile that's the way it's going to be, we can model it and we can mitigate the risk with wireline sticking with 99% efficacy. On challenging wells, some people are still using pipe conveyed logging. You can largely avoid that by teamwork between ourselves and the logging providers and the rig crew through technology integration. Pipe conveyed logging is risky, it's slow, and it's highly polluting. I think clients should review the wireline contracts to ensure that you always have a broad range of conveyance technologies. Have a workshop, tell us what's new. What are you thinking about? Do you have any new tech we can field test? You want the right tools for every job. Avoid set menus. Set menus can last for years, okay? The reason why people have gone fishing for those 96 post-mortems is that we were not on that set menu. The menu has to change. You change the menu, you're going to get better performance, okay? Definitely bespoke depth control procedures are needed for station logs, especially on deep water wells. And each well tool string mod system behaves differently, and the procedures should reflect that. Continuous temperature logging is a great opportunity in the post-mercury area. These extrapolated temperatures across the entire wellbore should enhance the well evaluation. And then lastly, I would say, having built a lot of hardware in the last 15 years, the future wireline risk management, as I see it, is not in hardware. There's plenty of hardware around to do a pretty good job these days on even challenging wells. It's about diagnostics, it's about data, and it's about simulations. When you're running technology in the hole, what data am I getting from it? What am I learning? Okay, are there any shortcomings? Is there a possibility to innovate? And AI is going to be involved. I can see it in formation testing, but it's going to need comprehensive data sets for training purposes. And I think that we should be in a position to provide that information on how far tools are actually moving compared to what the winch is doing, compared to what the cable is doing. So there's my summary on adventures in wireline research. If you've got any questions, you're most welcome. Ask anything.
Hey, Guy. Thank you very much for your presentation. Very interesting presentation. There are some questions in the chat. The first one is, do you already have experience running these tools in Brazil? What are the mitigation in case of get stuck, even using the standoff? Do you need a special overshoot?
Yes, you do. Yes, you do. One second. I may have a slide here. 1 second. I'll have to find the slide. All right. Slideshow. Can you see this fishing equipment?
Yes.
Okay. So basically, we do a fishing assessment before any project, and we look at the full string. That would be the fishing BHA that is available in country. We look at the drill pipe, we look at crossovers, and we choose the wireline standoff size according to the clearance of the minimum ID at the tool joint in the drill pipe. Okay, and we will provide a circulating sub with a no-go in it, such that the standoff can pass through the no-go, and then a hang-off sub, so that if that spear is dropped at surface, it will catch in the no-go. So there's 2 pieces that we send along that supplement the fishing kit that's already in location. Sometimes we need to send a circ sub, because that could be the spear that's sticking out the circ sub. You can't put your TRW valve on there, so we'll send you a longer circ sub, so that this spear is buried inside the box, and then you can circulate when you want to. But it's part of the early pre-job assessment, and we have a lot of fishing equipment that we've already made, so we can make custom gear, or we have stuff on the shelf that we can mobilize with the wireline standoffs. We haven't done any jobs in Brazil yet. We're doing some modeling on a project that's coming up. I can tell you that of the 370 deployments, around 5% of those, even with wireline standoffs in the hole, have had a degree of cable sticking, because if the hole is rough, if the hole is washed out, the standoff can't do its job properly. But what I can tell you is that it will reduce the sticking significantly, so that you can carry on and get the job done. Okay, so we've had 15 runs with cable sticking with standoffs in the hole. 10 of those we managed to continue with standoffs. 2 of them, the client got nervous and said, I don't like these overpulls, get out of the hole. And 3 times we have fished cable with standoffs. So we've stripped over them 3 times. So the fishing rate is around 0.8%. Okay.
Okay, thank you, Guy. Another question is, do you have experience in very unconsolidated sandstone, in well with higher inclination, higher than 70 degrees?
Yeah, we've logged wells in the Gulf of Mexico between 50 and 100 psi. Very, very, very soft formation. The deviation is not some. We've logged up to around 60 degrees, something like that. I mean, standoffs are not a descent aid. They're not going to help you get down hole, but they will help you get out of the hole. But it depends on the nature. If there's an open hole build, that's building to 70 degrees, I can tell you now that you've got cable sticking risk. And so we would put the standoffs over that build section to make sure that when you finish your stations, you can move the cable and you're not burying yourself into that high side dogleg. If that 70 degrees is a tangent and all the work was in the behind casing, you're probably not going to need wireline standoffs unless you've got sufficient directional instability to create small doglegs, to create thrusts that will then cut through that mud cake on the low side of the hole, and then you may have differential sticking risk. And it also depends, if it's an ultra deep well, and we can run 10 standoffs that take 15 minutes to install. Are you really not going to run wireline standoffs as a mitigation? Common sense has to prevail. There are some wells where you want to do absolutely everything you can to mitigate those risks, even if the benchmarking says, well, it's marginal. You may have this, you may have that. Every well we could write you an essay on what could happen. Right, but clients don't want essays, bullet points. They want charts. They want things that they can make decisions on. And so that's why in the software we try to condense everything into something that is easy to digest, and people can make a decision on that.
Okay. Another question is can this depth control technology be used for usual LWD wireline lock, making it easier to make that correlation between different runs?
I can't say. I think in principle, yes, but it depends. It depends on. So effectively, what we're saying is that in some situations, so in the Middle East, there are some wells where it's a tractor job, okay? It's horizontal, and the cable stick slip is so bad that they can't use the data that's from the tool because the recorded depth is from surface and it's not reflecting at all what the tool is doing. And in that case, we could use our depth instrument to provide a downhole depth channel. So you're using your cable for power and you're using it for pull. Okay. The thing is that some of those tools are using memorization and they need the data that's coming from the winch real time in order to put data on depth and do processing and things like that. Okay. But I think what would be very interesting is to do 2 or 3 side-by-side runs using the wireline, primary depth reference, correlation, making correlations, tying in, and then having an independent depth channel with a gamma ray that reflects what the downhole depth recorder is saying. I think that would be very interesting.
Okay, thank you. The last question is any plan to have the temperature sub for LWD applications?
For LWD?
Yes, the temperature sub sensor.
You mean inside some sort of drill collar or something?
Yes.
That is possible. I mean, there are existing solutions already available, and I would argue that they have probably got better vibration and shock robustness compared to something that what we could do. Okay, but the temperature logger that we're building is pretty small. It's a 4-wire compensated RTD going up to 175 degrees C, plus or minus 0.75 degrees C. It's a low cost unit. If you build a 175C RTD, the components are going to cost you around $2,000. Okay, and because it costs you $2,000, you're going to be very reluctant to junk it. You're going to keep running it, and then it's going to fail, and then you're going to say, okay, it died. The thing that we're building is less than 10% of that. Okay. And so what we're going to do is have a low-cost replaceable logging board. We download the data, we look at the heat cycles, and we will come up with a metric for changing it. If we get 5 runs at 175 and then we decide we're going to junk it, or we get 10 jobs at 135, you know, it's all monitored, and we can replace those boards. So our approach is different to what people are normally doing. You know, there's an outfit in Austin that's getting 400 hours at 175 C from components that are 125 degrees C, and that's the route that we're going. Okay, so you don't necessarily need high dollar components. We could make something that basically you put it in the hole and then you're going to junk it after the run. You know, if somebody's interested in that, get in touch, and we'll have a look at it. But there are other people who are specializing in MLWD equipment, which is going to be a lot more robust than what we could do.
Okay, thank you very much, Guy. On behalf of the Brazilian chapter of the SPWLA, we want to say thank you for take the time of share this presentation, very interesting presentation. Just to say thank you, okay? So, para as pessoas que assistiram a palestra, muito obrigado pela presença de cada um de vocês. E a gente, o próximo mês teremos mais uma palestra. Obrigado e boa tarde para todos.